That's
I guess.
that's the flavor of the
All right, how are you guys doing? Let's start talking about some astronomy. Actually, we're going to talk about homeworks. And let's see, everybody got the homework in? No?
Yeah.
There's a couple of you are missing. So, okay, once again, this isn't the habit that I planned on, but it's the pattern that has arisen. I haven't actually finished grading it yet, so real quick, if you want to get it in tonight, get it before I start grading, and I'm going to start grading it first thing at like 8 o'clock tomorrow, so a little bit of an extension. I'm going to go over it now, so everybody should have their ducks together. So take good notes, and if you didn't get something right, go back and fix it up. Yeah, so as a classroom strategy, I'm curious with exploring this, going over the homework and then giving everybody an extra chance to actually do it. So last time, I made sure, just because that's how it happened, I made sure to get the video up right away. But then the next day, everybody turned it in. There was like 6 or 7 of you that hadn't turned it in and then turned it in, but nobody watched the video. So so I feel pretty all right. Like you guys are just paying attention in class and then did the problem. So I'm happy about that. So anyway, really I want you to do the work and put your hands on the things, because putting your hands on the problem is way more important than watching me do something. So that gets you a little bit of an edge to help finish the homework. Maybe we'll do it that way. Okay, so let's see, homework. Oh, I didn't turn that thing on. I should do that. First homework problem, I'm going to fire it up. The first homework problem was find the binding energy of a sphere. Everybody do okay on that one?
I think so.
Does anybody have any questions on that one? Yeah.
I just thought I got too many years.
Was that?
Like for the lifetime of the star.
Oh, yeah, we'll talk about that one next.
Yeah.
We'll do them in order.
I got way too many years on the big lifetime stuff.
Okay.
This is like the 40s.
I know we were supposed to get like kind of 40th or something. I did not get that. I don't know why.
Well, I got some, you're supposed to get some of the 40s for the small ones. And
Like 10 to the
like millions for the big ones, but
Oh, yeah, I'm
I
not
just got
fucking-
10 to the 40s.
Did you search up?
So
Let's
this
set
is
things up
the
correctly.
blind leading the blind here.
Yeah, and further up the chain, it doesn't get much better.
The actual one was like 10 to the 4 times bigger, so the number was even smaller.
Why does that not work? No, that's not the right thing. Is this the right thing? No, that didn't work.
So
Okay.
if I were to help you, it would just be like, make the same mistakes that I made, and take
Maybe then we'll get somewhere.
I don't have.
Yeah, my mistakes are clearly the correct mistakes.
So like obviously.
Obviously. We're not equally
Right.
making mistakes here. But clearly I'm right
Yeah.
in how I messed up.
Yeah.
All right. Okay, here we go. Now we have to have the thing. So, now, compute the binding energy of a sphere in... I'm moving around. Sorry, I didn't set my stuff up the right way. So, compute the binding energy of a sphere. I'm going to just go through and do this kind of quick. Over there. Okay, just so that we've covered our bases. Let's see, what are they doing? I like the puzzle of trying to figure out what they were doing in class before I got there. That looks like thin films. Or the reason why dirt on the road looks like a rainbow. That's what that picture shows. Where is my eraser? Here it is.
I can't
Okay.
tell if that's very insightful or like completely random.
That this is why things look rainbow. So if you have a thin film of some material, then you're going to get interference inside the material as things get reflected around. So some wavelengths will cancel out. So if you have like an oil slick on water, it'll look like a rainbow because of this. Because if you've got a thin film, and one of your paths will be longer than the other one, so a lot of your wavelengths will get will get canceled out because there'll be a path shift. But that depends on the geometry, so it looks like a rainbow. Anyway, that's why rainbows happen. Okay, so binding energy of a sphere. So this is super useful. It's a super useful thing to know how to do and be comfortable with doing. So the binding energy of a sphere is minus gm rho over r. And then I need to integrate this from 0 to r. Let's actually write this a little differently. Let's write du and dm here. So this is now saying a tiny little bit of mass and a tiny little bit of potential energy. That way that makes sense, right? So then it makes sense to integrate from 0 to r. So then this turns into, we got 0 to r, g times m. What is m? M is 4/3 pi r cubed times the density. That's familiar to everybody, right? Volume is 4/3 pi r cubed. G, so then we've got a 4/3 pi r cubed rho. And then I've got a rho, that's my dm. And then I've got the volume integral, because this is a sphere. I've got a 4 pi r squared dr. All of that is over r. And I got a minus sign. Okay, everybody happy so far? Writing down the integral is the hardest part of most physics problems, because a lot of times that's good enough, because sometimes the solution that you have is, hey, there's this integral. I don't know how to solve it, but I know it's the answer. However, we can continue and solve this. So let's collect all our terms. So I have a 4 and a 4 and a pi and a pi and a rho and a rho. And they're all constants, so they come out. So I've got 4 squared, pi squared, rho squared over 3 and a g. And what's left on the inside, 0 to r, is just r to the 4th. 1, 2, 3, 4, 5, minus 1 is 4. R to the 4th, dr. I do this integral, and that gives me 1 over 5 r to the 5th. So then this 3 turns into a 15. And so I've got now g times 4 pi rho squared over 3 squared times 5, and I need another 3 up top. Because I don't actually have 3 in the denominator. I only have 1 3 in the denominator. I need 2 3s in the denominator, because I'm going to make a mass. So I put another 3 here, and then I get another 3 here. So here's where my 3/5 come from. So now this bit is now 4/3 pi rho squared times 3/5 times g and a minus sign times r to the 5th, but r to the 5th is r to the 6 over r. So I can throw in an r cubed inside of here. There's my r to the 6 divided by r, and I'm left with minus g times 3/5 m squared over r. Everybody good with that? So setting it up is step 1. Actually doing the integral is step 2, and that's mostly accounting.
What happens to the 4
Which one?
in the last line?
Here?
Yeah.
That turns into the mass. 4/3 pi r cubed
Oh, okay.
times rho is the mass. So this is my mass. Probably should have left that up so you could see it while I'm talking about the next thing. What's next? Okay, prove that for an adiabatic process, P equals some number times rho to the gamma. So I had a bunch of crap to do this morning, so I didn't get a chance to actually look at what anybody did. So how did this one go? The second one. Oh, I'm sorry, I forgot about 1B. Let's do 1B. Okay, so I have some energy, which is 3/5 gm squared over r. How do I sort out how long it will last? So I divide this by the luminosity. T is E over the luminosity. And the luminosity is just the solar luminosity.
I don't know where you got it from.
So you should have gotten a number that's like 3 times 10 to the 7. Yeah.
Is E over 5 or over 10?
Oh, so okay, that's a good question. Okay, so this is a factor of 2 that when we're spitballing things doesn't matter a ton. But he's got a good point, and the way the book argues, the book says that this is the total energy, but you only get half of it because as you're thermalizing things, half of that energy can turn into something else, but half of it has to remain as thermal energy. Because we always have to be in virial balance. So because of virial theorem, twice the kinetic energy is the potential energy. So if we just think about the energy that we can get out of the star is going to be the kinetic energy that's of the stuff rattling around, right? That's where the energy is going to show up. So that's how much we have available. So there's a factor of 2 different from what I put here, so that'd be 1.5 times 10 to the 7. But you should get something that's like 10 to the 7 years. Is everybody good with that? Okay, so the second bit, the next bit. Proving that this is an adiabatic, this is true in an adiabatic scenario. How do you guys feel about that one? Were you able to get through the process? Not as much?
I think so.
You think so? Maybe it's a little dodgy? All right, I got some no's in there. Okay, let's go through it slow, and I want you to stop me when I stop making sense. So we start with the first law. So the first law says du is dq minus pdv. So all of this says is the energy that's inside a thing, if the energy inside a thing changes, it's changed by heat flowing out or work being done. It's just accounting. Those are the only places that you can put the thermal energy. You can either leave or you can do something with it. So we also know that PV equals nRT. And we could turn this into a differential equation by saying P dV plus V dP equals nR dt. This is just product rule. So these are the 2 things that I need most. So adiabatic, what does adiabatic mean?
No entropy.
So there's no entropy, or no entropy change. Also, there's no heat flux. So remember those 2 things are related. So adiabatic, ds equals dq over T. So no change in entropy means no heat flow as well. So that's the important bit. A lot of times when we say adiabatic, what we mean is no heat is flowing in or out of the system, or the system isn't interacting with the outside very much. So because of that, then we can say that du equals minus p dv. That's just taking this and getting rid of the dq. That's easy. We also know that du is equal to cv dt. I need to get rid of some variables. So right now I've got, how many variables do I have? I have pressure, volume, temperature, and internal energy. So that is too many variables. I have to focus on. So du is cv dt, that gets rid of the u. That's great. So then that tells us that so this tells us that minus p dv equals cv dt. So the easy way to write this is to say that dt equals minus P over CV dV. So now it's just a thing I can plug in. So I take this and I stick it into here, and I'm left with P dV plus V dP equals NR P over CV dV. Everybody good? Does this make sense with everybody?
Is there a negative there somewhere?
Yeah, there's a minus under there. Thank you. So now, so the other piece of information that I need is that that CV plus NR equals CP, and CP over CV is this number we define as gamma. I don't really care about CP and CV individually, because they're related by this thing. What I really care about is gamma, which tells me how squishy the gas is. So we put this CV everywhere else, and we've got CVP dV plus CVV dP equals minus NRP dV. I'm going to take this guy and put it over here, and I'm left with CV plus NR times P dV equals, and then this has got to go to the other side, CVV dP. Everybody on board so far? So I'm going to take this CV and put it over here. And then this is, now we're jumping ahead, CV. This whole thing right here is just this number gamma. So we've got gamma P dV equals V dP. Okay, is everybody on board still? Anybody not understand any of the pieces with how I got to this part? Yeah.
It's CV plus NR over what?
Over CV.
Over CV again?
Yeah. So I have, in this line, I have a CV, a CV, and an NR. So this comes over here, because this is both a PdV and a PdV. So this NR comes over here and it hangs around with this guy. And then we divide through by this CV to get a CV underneath everybody. So then that's how this turns into gamma. Then we solve this by, I'm going to divide through by V times P. So then I'm left with gamma 1 over V dV equals 1 over P dP, and I dropped a minus sign. And then I can rewrite this is the other weird step. I can rewrite this as gamma d log V equals minus d log P, and now this is a full derivative of on both sides. All right, I can take this gamma up here. Then now I've got two full derivatives. D of a thing, that's a full derivative. So I can just integrate, and I'm left with V to the gamma equals V to the minus gamma. This minus 1 goes up here, equals P. Or V to the gamma times P equals a constant, or P equals a constant times rho to the gamma. All of these are equivalent ways to write this down. So there's a whole bunch of physics in this. So I'm going to just give it a drive-by real fast, just because there's a lot of physics. So the first thing to know is ideal gas law. Second thing to know is PV equals nRT. The third thing to know is that du is CV dt. The fourth thing you need is this bit about CV plus NR equals CP, and also CP over CV equals gamma. So that's the fourth thing that you need to know. So once we've collected all these pieces of information, then we just do some calculus. And do the chain rule a couple of times and rearrange things to get rid of stuff. The chain rule to get rid of variables. And then we get something that looks like this, and then we integrate it with that. Does anybody have any questions about this? This one may or may not show up on Friday. So make sure you understand it.
Okay.
I will have office hours tomorrow for discussing of such things. Okay. For a sphere of gas, show that dPdr is minus gm of r rho over r squared. So that's relatively painless. The cheap way to do it is just to say that force is minus grad p, and force is also gm rho over r squared, and you equate the two and you're done. That's really all I'm looking for, is pressure gradients give you force, gravity gives you force. You equate those two things and you're finished. So this equals dr. So then the next bit says, show this much more simple looking thing. dp d tau equals g over a kappa of r. So I don't have dp d tau, but I have dp dr. And I know from chain rule, dp d tau is dp dr times what? What's the next part? Somebody else? I know you guys know how chain rule works.
dr d tau.
There you go, dr d tau. Not that I didn't like yours, I just wanted to hear from someone else too. So dr d tau, okay, chain rule. Think about it like a fraction, like the r's have to cancel. It's not really how it works, but think about it that way, because dimensionally that has to be how it works, because the units have to cancel. And dr d tau, well, what's tau? Tau is kappa times density times r. So dr d tau is just 1 over kappa rho. And dp dr we already established is minus gm over r squared, but this is just little g times rho. So little g is gm over r squared. This is the acceleration due to gravity. Now we can put a minus sign here. I think the way I wrote it implies that there's a minus sign here because I wrote it as a positive on the right-hand side. So g has to be defined with a negative here, just like it was. We're missing a minus sign. So this is little g. So this is equal to little g times rho. So dp dr here is little g times rho. So this is just equal to little g over kappa. Nice and simple. So it's just the acceleration by the opacity. So the change of pressure with respect to optical depth is just the acceleration relative to how photons have to get around. Any questions on that? Everybody good? Hydrogen burning lifetime of stars for big and small stars. So how do you do this?
You take the PP chain, and you take one side. You add the energies for the reactants on that side, and you take the other side. You add the energies for the products, and then you take the products and subtract the reactants.
That's good for the next one. I'm talking about the problem above that one. I had skipped.
I saw the next.
Yeah, no,
I'm sorry.
No worries. You're just juggling. So I will just accept that as an answer for when I do the next one. So this one, how do we do this one? We pretty much did this one already, right? So you've got some energy divided by some luminosity. So what's the energy? We got to sort out the energy. The energy is going to be the efficiency times the mass times c squared. And the luminosity is just going to be the luminosity of that star, which I gave you. So for the first one, the efficiency is 0.007, 0.7%, which is really not very high, but there's a lot of energy used. The mass is 0.072 solar masses. This is a pretty little star. This is almost a Jupiter. But it's big enough to be considered a star by itself. So the total energy is just going to be epsilon times m times c squared. And the total luminosity I gave you is 10 to the minus 4.3 times the solar luminosity. Then you just plug in some numbers, and you get something like, was it 10 to the 14 years? Is that what I got? Let us.
Which one?
It's not up there.
No.
That's the small one.
14. Oh, I thought we were supposed to get 10 to 40.
I got 10 to the 40.
40's a lot.
I thought you said for like a small star, they're supposed to
For
live
the
forever.
small
Yeah, stars live forever. 10 to the 14 years is a long time.
Oh, okay.
10 to the 40 is a lot longer.
10 to the 40 is longer.
That makes more sense, because I thought you said 40 is the whole time, and I was doing the problem over and over again. I was like,
Okay, so I screwed something up. Well, I knew I had problems on that one anyways.
Very. What the hell?
I don't know. I can't believe I said the answer to the problem.
Oh, you gotta stop. You gotta look at that. You gotta just let that one go.
What? Okay.
It's totally cool.
It's the social anxiety.
Yeah, I know. You're allowed to let that one go. Just let it go down the river. The river of history. Nobody has to think about that again.
My brain don't like it though.
That's all right. We'll just latch on to this next thing.
Okay. Yeah. It's okay. Now I'll worry about getting the problem wrong.
Yeah, there are so many bigger things to worry about. Where am I? Let us fire up some numbers. There are so many things to worry about. Don't worry about that. Worry about the other things. I'm really good for helping people with their social anxieties. I'm just pulling up my numbers because that's where I have actually my numbers.
So it is R. I think it's what we do is well, I don't know why I have S.
Give me my stupid numbers. Okay, yeah, I get 1.49 times 10 to the 14 years for the first one, and I got 8 times 10 to the 5 years for the other one. So the other one is the same process. Put my chunk up. Is the same process except for the mass, same efficiency. The mass you use 85, but I told you that this one only gets to have part of its energy, or part of its mass that actually burns. So this is 85 times 0.1, because only 10% of the star can burn. Why is that? Let's back up for a second. So when you got really big stars, they tend to be radiative. When you have little stars, they tend to have convective. They tend to be fully convective. Why is that? Because when the temperature is hot on the bottom, it convects. So why do little stars convect?
Everything's closer to the bottom.
Well, yeah, but they're cooler. They're smaller. Because they've got this
Is
crazy
this
thick
distant?
atmosphere. So you've got this atmosphere on a little star. Remember, the atmosphere is cool, so you have all of these excited states that are all populated. So there's a lot of place for the photons to run into potential ions. So a smaller star has a cooler, therefore optically thicker atmosphere, therefore they convect. Therefore the whole thing rolls around. That means that when I'm convecting, I can suck up all of this hydrogen, bring all this hydrogen back down to the burning spot. It's only burning in the center. But a bigger star is radiatively dominated because they're not convecting. So all of those photons can just leave by radiation, so they don't convect. So that's the big difference here. Is the more massive star, the burning's confined to the center part. So that's the importance of this 0.1. So while this is innocuous, and I do say I hate numbers, I want you to try to get your head around why we only get 10% of that star. So 85 times 0.1, and then the luminosity is 10 to the 6 times the solar luminosity. So you get a bit more mass and a lot more photons. So for this, you do the same stunt, and you get something like 8 times 10 to the 5 years, which is really not very long. I mean,
It's longer than I'm gonna live.
in principle.
Not that attitude.
I mean, you're only immortal until you die.
What?
This is
Yeah,
true.
that's accurate.
Wait, what value do you use for the luminosity of the sun?
I used L sun.
Amazing.
We barely lost a couple weeks ago.
Yeah, so either has lost or is losing.
8.36 times 10 to the 26 watts.
Honestly, I'm with you.
I use the same thing.
That's all good. I'm not super worried about little numbers, so you got a calculator error probably.
This is astrophysics. You can wave so much.
Yeah, I'll forgive everybody a factor of 2, unless it's an important factor of 2. Sometimes they're important. Like in the virial theorem, if you screw up the factor of 2, I'll take a lot of points off.
Oh, yes.
Aw.
This is
Okay, so for the next one, oh, did I get everything? Does anybody have any questions about this burning lifetime? Big fat stars don't live very long. That's one of the big key takeaways. What does that mean for supernova? It means the big fat stars go supernova really fast. The little tiny ones really don't, if ever. Okay, so for the following, using these masses, compute the total reaction chain for the PP chain. So let's see. So this, so did anybody have any questions about this one? I think we've gone over what to do. So we have stuff goes to other stuff, right? So we compute the mass of stuff, and we subtract off the mass of other stuff, and this is the energy that gets liberated by the reaction. And that energy is either positive or negative. And the PP chain, did I write that down in a way that makes sense? I'm going to make this bigger so I can actually see it. Here we go. So here's how the PP chain works. So here are the masses. We have the mass of the proton. We have the mass of the deuteron, which is not quite twice as big. But the mass of the electron, which is way smaller. Oh, and that's a units issue because what I was working from was broken. We have the mass of helium-3, which, ignore how I computed it. I had to compute it this way because what I was doing was, I was cheating. So we have the mass of helium-3, which I gave you, and the mass of helium-4, and the speed of light. So you can just use these numbers here, 938 for the mass of the proton, 1800 for the mass of the deuteron, 2800 for the mass of helium-3, and 3700 for the mass of helium-4. So these are all in MeV per c squared, because that way when I multiply by c squared, I get an energy, right? This is a common thing, so a lot of times you'll see the mass of the proton just written in MeV, because c is 1. So how does the PP chain work? So the PP chain first starts with losing its chalk again. There's like a wind of chalk away from the board. Okay, so the PP chain starts with a hydrogen plus a hydrogen, which goes to a deuterium plus a positron and an electron, and a neutrino. So if I work out the mass, so this is twice the mass of the proton minus the mass of the deuteron minus the mass of the positron should give you oops. Let's make it tell us something useful.
Let's try.
Let's see. What are you saying? Okay, so the first step loses 0.4 MeV. So in this step, that gives us a half an MeV, which is about an electron. So on the second step, you take it's the chalk wind. You take that deuteron plus another proton, and this gives you a helium-3 plus energy. Yeah, okay. Do I need to do any nuclear? Am I going to get a positron or a neutrino out of this one? I'm not. Why?
Because it's a GAM.
It's not a count.
It's a different type of.
I got the same number of protons and neutrons on both sides of the equation.
Okay.
So you just add up all the tops and add up all the bottoms, and if you get the same number, then you don't need any positrons. Right? So here I got 3 on the top and 2 on the bottom. Whereas here, I got 2 protons, but only 1 proton in the end, but 2 deuteriums, but 2 neutrons. So here, for the first one, I convert a proton into a neutron, and that's how you get a deuterium. So that conversion gives me an E plus and a negative. So for this reaction, we need to measure the mass of a proton plus the mass of a deuteron minus the mass of the helium-3, which gives us a number of 5. We get 5 MeV for that. Then in the third step, now I have a helium-3 in the pp1 chain. I take 2 helium-3s, and I get a helium-4 plus 2 protons plus, let's see, do I do any nuclear conversion? I do. So I've got to get a positron and an electron again, because once again I'm converting something to a neutron. So I've got 4 protons to start. I got 4 protons in the end. This one doesn't get a neutrino. Now it just does that. Good. Learning things as I do. So the last one, you get 11 electron volts. And maybe, right. And then for the total step, how much energy do I have? So if I wanted to know the total energy, if I call this one E1, and this one E2, and this one E3, right? This process has to happen twice. And this process has to happen twice, because I need to have 2 helium-3s. So that's where I get my 4. So I do this twice, and then I do this again. That's how I get my 2 heliums. So the total energy is going to be twice E1 plus twice E2 plus E3. You should get like 30 electron volts. Questions? Everybody happy? And then the last one. Oh, am I on time? Oh, good. The last one, I've only got a couple minutes left, and I do want to talk about what I think is going to be on the test, because I have special insight about such things. So for the last one, I say, let's sort out what what the cross section and opacity of H minus is. So remember, H minus is this ion that's a proton plus 2 electrons. So you need to know what the opacity of this is. The reason we have that is because there's so many free electrons. We get a lot of free electrons, so they get sucked up by the hydrogen. So someone smarter than me sorted out that the opacity of H minus is 7.9 times 10 to the minus 34 times the metal fraction normalized by 0.02 times the density to the 1/2 and the temperature to the 9th. And this is in meters squared per kilogram. This unit, let's think about this unit for a second. This is an opacity. Opacities are always in area per mass, because the opacity is the cross-section per unit mass. That's why we always have a rho kicking around. So this ought to be meters squared per kilogram. So all your opacities ought to come out like that. So how do you make this work? So to make this work, it bugs me the way he wrote this, the way they typeset this, because, I don't know, whenever I try to typeset an equation that's got numbers in it, I always try to tell you what units I used. You've got to use kilograms per meter cubed with this one, and Kelvin for the second one. If you use centimeters, you'll get a weird answer. So I gave you a density. I gave you a number density, which is 10 to the 23 per cubic meter. Which gives you a mass density, which is MP times the number density of 1.7 times 10 to the minus 4 meters, kilograms per meter cubed. Which is a low number. And T, I told you, is the temperature of the sun, 5777. So you plug all this in and you get an opacity of 0.07 square meters per kilogram. Is everybody okay getting to this? All right. So then, what I wanted was the mean free path. So L equals 1 over kappa times rho. We would just plug in this and this, and you should have gotten something like 84 kilometers, which is pretty far, actually. Fair enough. That's close enough. 81 is 84. It's close enough. I use the convention 4 pi equals 1 a lot in my work too, so I like nonsensical things. And from a similar equation to this, we know that sigma equals n times L. So L is 1 over kappa rho, which is the same as 1 over sigma n. So we want to get the cross-section, we'll just invert that, and I got 1.2 times 10 to the minus 28 meters squared. All right. Does anybody have any questions about this homework? Good. Let us talk for a moment about, I got 4 minutes to write all of this stuff on the board.
Oh, dear.
Can I take a picture
Of this? I will take, what?
Take a picture of it, yeah.
You can take a picture of this. This is my chicken scratch, which is not legible to anybody else.
Mood.
And I will, if I remember, I will put this up in a slide. Odds of me actually getting to that are small, but I'll try to do that. Okay, so what's on the test? So focus on homework 4 and homework 5. Also think about the other ones because everything stacks. It all stacks up. So I can't talk about these things without talking about the things in the previous ones. So do make sure if there's something that you're dodgy on in the last ones, to go pick that up as well. But these are the important bits. And we talked about chapters 7, 9, and 10, or 11 if you have that other version. So the main topics are binaries, atmospheres, and interiors. And we also talked a little bit about telescopes. But the only thing that I really care about is the diffraction limit.
Weren't telescopes on the last test?
I think the homework was on, I think the telescope, I think there was a telescope question on P4.
Yeah.
Oh, with it's optical thing.
Yeah,
The
no.
angle.
It's just the
angle
it was the
question.
resolution question.
Yeah.
I just mixed up what I.
Yeah, it's all right.
No
So,
work.
It's just that one
I,
formula.
okay, so let's start with the easy ones. Telescopes, the only thing that I really care about is the resolution is 1.2 times lambda over d. It's the important bit. For binaries, I'll give you orbital parameters and you tell me masses. It'll be algebra because I'll tell you some of the masses or some of the things, and then so the important bit with the binaries is to remember how to work with the period axis relation. Kepler's law. The squirrels were very slow bringing Kepler. So with binaries, the only thing I really care about is getting masses, because that's why binaries are so important. Binaries are crucially important for the development of astronomy, because that's how we got to measure masses of stuff. Between binaries and parallax is really how we have all of the understanding we have.
What does that say?
Which?
Squared.
P squared is 4 pi squared over GMA cubed. That's just Kepler's.
A cubed in the denominator? Or?
No, it's upstairs.
Okay.
So then the other two, okay, so that's simple and that's simple. Those are all pretty simple. The other two are the complicated ones. So in atmospheres, what did we talk about? And what am I on time? Oh, I got 1 minute left. Okay.
You got more than that. That's fine.
Yeah. You know, I try to be respectful of your space and whatnot. Oh, also types of binaries. So go read up on the different types of binaries. The only thing that they tell you is what can you see, because you can't always see both stars. Sometimes you can see the spectrum, sometimes you can see the motion, sometimes you can see the spectrum of both, sometimes you can see the spectrum of only one. So think about the different types of binaries. Even though there wasn't a question on it, it's a pretty low-hanging fruit for interesting questions. Okay. In atmospheres, di equals minus kappa of rho I ds. This is the radiative transfer equation. We'll just leave it like that for now. This is a radiative transfer without any sources. So be familiar with what that is and what everything in it is. So this is the radiative transfer equation. We spent a little bit of time with it. Be able to solve it. When you solve it, you get I equals I naught e to the minus tau, and tau is kappa rho L. L is the length of the cloud. This is the optical depth. So we use the optical depth both as like a parameter, but we also use it as a coordinate because we can change it to the length. We talked about mean free path. L equals 1 over kappa rho equals 1 over n sigma. Think about what mean free path is. Think about what kappa is. Think about what sigma is. We talked about optical depths. We talked about types of opacities, or sources of opacity. And these were bound, 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 free, free, free. And then we also talked about Thomson our electron scattering. That's where our H minus shows up. Or sorry, and then H minus, those are different things. Thomson is free electrons, and H minus is that ion. The ion's bigger than the electron, so this cross section is bigger. So those are the sources of opacity. So make sure that you're familiar with what each one of these things mean. Again, even though there wasn't a homework on it, this is just like trivia that you just read in the book. Just read this section and familiarize yourself. We talked about the Roslin mean opacity. I'm not going to ask you to compute that or anything. It's very difficult to compute. But you should know like what it is. More importantly, Kramer says that opacities go down like t to the 3.5. Be familiar with that. Let's see, we also talked about line broadening. I didn't make you do any homework on it, and it's stuff that you got to really work on to get your head around. So those are the things that we talked about for.
So are we likely to see a line broadening thing?
No.
Okay.
Odds are low. I didn't spend a lot of time on it. So when you're like, should I spend some time on this? Think about how much time I spend in class and whether there's a homework on it. Those are the two things that you should look at. Homework problems and the amount of time I spend talking about it. I spent a little bit of time with line broadening, so I do want you to be familiar with it, but I'm not going to be asking you a hard problem about it very well. But be familiar with, so there's three kinds. There's natural, and there's Doppler, and then there's pressure broadening. So the natural broadening is just the uncertainty principle. Doppler broadening is stuff moving around. And pressure broadening is stuff banging into each other. And the Doppler broadening is by far the most important of these. For what I do, I don't know, pressure broadening is actually probably important if you do atmospheres. Okay, so that's interiors.
Was that interiors or atmospheres?
That was atmospheres.
Oh.
Yeah, so the atmospheres are about light going through things, because the atmosphere is just a thing that's in the way. And then interiors. Okay, so basically everything in interiors is setting up 4 equations and talking about the nuclear burning. So make sure you're familiar with all of the 4 equations and where they come from. And if I didn't ask you to do a derivation, I'm not going to ask you to do it on, I'm not going to ask any long derivations on the test that I haven't asked you to do already. Long ones. There might be. So the 4 equations are pressure, we'll write big. dP dr equals minus gm rho over r squared. This is the force balance law. We have the continuity law, dm dr equals 4 pi rho r squared. This one is nice and simple. But the luminosity, dl dr, this one is also simple, 4 pi r squared rho epsilon, where epsilon is the source of the burning. So this is a complicated thing that we'll talk about in a second, but it's just a number. It's just a function of pressure and density. Here in the way. And then the temperature gradients changes based on whether or not the star is convecting. So if it's not convecting, then you're left with radiative, 3 over 4 AC kappa rho over T cubed, luminosity over 4 pi r squared. So this is for radiation. And if it's convecting, oh, there's a minus sign there. If it's convecting, you get 1 minus 1 over gamma times G m rho, no, Gm over r squared times mu
1 minus 1 over what?
Gamma. And then we talked about several different kinds of burning. So we talked about the PP chain, and you should commit to memory the first one. If you also know the other two, that wouldn't kill you, but odds of there being a question on that requires you to know PP1 are pretty high. So make sure you're familiar with the PP chain. Make sure you're familiar with the CNO cycle. And the other thing we talked about was the triple alpha process going to carbon. We'll talk about oxygen burning next. So the book talks about oxygen burning, but we're not there yet because nothing's burning oxygen yet. We'll get to massive stars and burn oxygen. We'll get to explosions and burn oxygen. So understand what they are. Understand how the efficiency is. So the burning rate is equal to rho times T to some number, alpha. For PP, alpha is 4. For CNO, alpha is 20. And for triple alpha, I don't need an equal there, alpha equals 41. So some of these are incredibly sensitive probes of the temperature and incredibly sensitive on the temperature. Let's see. Transport, I skipped a bunch of stuff.
So PP chain is more efficient than like triple alpha?
They do different things too.
They do different things.
And they burn at different temperatures. So PP chain burns at like 1,000,000 Kelvin and triple alpha is like 1 billion or 100 billion.
Right, since you mentioned efficiency.
Yeah, so the burning rate is the thing, not efficiency.
Okay.
So we didn't really talk about efficiency, we talked about burning rate.
Is that 41?
Yeah.
And what does the radiative equation say?
Where?
For the 4 equations, dTdr is for the
dTdr is all of this stuff. It's better to just look it up in the book.
Okay.
You don't need to clone it there. Just look it up. That's a better place. There's 2 of them. One's for radiation, one's for convection. I think that's it. Oh man, I went 10 minutes over. Thanks for putting up with me going over a little bit. And I'll talk to you guys soon.